All right, let's jump into setting up an example. So I've got a demo case here. It's just a generic rockbox type transfer chute design, and we'll use this to look at some basic setup of an analysis and post-processing. Now, whenever we are performing an analysis, one of the things that we always have to do is identify the goals of the analysis, why we are even performing the analysis in the first place, and what are the metrics, the quantities or qualities of interest that we're looking to extract. And of course, we have to identify the operating conditions, both from a bulk materials standpoint and also a system/geometry standpoint. So let's take this hypothetical example. I've got 8,000 tons per hour of material. Let's say this is iron ore feeding into the transfer chute system. It's dry iron ore, so the moisture content is sufficiently low enough that we can essentially ignore any sort of cohesive behavior that isn't driven via mechanical interlocking. And as listed here, we want to make sure this design satisfies throughput requirements. We want to reduce the wear on our liners and belt. We need to ensure, of course, that the material is loaded centrally on the receiving conveyor. And at the end of the day, we want the most reliable design, functional design. We want to minimize design complexity. So let's go ahead and walk through the analysis setup and, of course, some of the basic post-processing. So I'm just going to switch over to this screen here. Now, when it comes to pre-processing in Rocky, it's essentially a top-down approach from the data tree. So we'll start off by defining some of the physics, and we'll leave all the settings in the gravity tab to their defaults. This is a dry material, so I don't need to switch on an adhesive force, but what I do want to do is switch on a rolling resistance model to the type C model. So moving on ahead, I'm going to switch on the boundary collision statistics module as well as the interparticle collision statistics. So those are just going to control some of the data that will be written to the disk that I will have access to for post-processing. So I'm going to switch on from the boundary collision stats, forces, stresses, intensities, and maybe we'll be interested in frequency of collisions. For the interparticle collisions, let's just switch on power and force. Moving ahead, let's import our geometries. So I'll just take all of these, set the units to millimeters, and we can double check that that's all sensible, that scaling, by making sure that the geometry limits are also sensible. So that looks reasonable to me. I'll hit OK. Yep, that's looking good. And I'm just going to switch the feed conveyor template on. And you'll see here that the feed conveyor, or the default feed conveyor, is essentially a pre-made geometry for all Rocky users. And it has a number of different attributes that we as the user can customize. So take, for example, transition and loading lengths. I'm going to change the belt width to 1.6 meters. Yeah, that's looking fine. Let's change the incline angle to maybe something like 3 degrees, and we'll sort out this offset. But it's going to be easier for me if I just change the head chute to be transparent, and we'll be able to place our feed conveyor much more easily. So vertical offset, looks like I'll need to make that a little bit higher. Horizontal, try 0.55. And you can change skirt board feeder box designs, for example, to take that up to 2 meters. The head pulley will bump this up. Face width going to be 2 meters, and bring that up to maybe 0.6. And if we scroll all the way down, we'll find the belt motion. And here the default is 3 meters per second. I'm just going to bump that up to 5 meters per second. Okay, so that's looking good. I'm going to keep going on down the list, and we need to set up a motion frame now for the motion of the receiving belt. So I'm just going to right click, create that new motion frame, and we'll set that up to be 2.5 meters per second in the global Z direction. Then I'll need to attach that, of course, to the receiving belt. I'll just rename that to something a little bit more sensible. Receiving belt. Okay, of course we can create new materials, change their densities and stiffnesses and whatnot, as well as prescribing materials interactions. So things like friction coefficients, coefficients of restitution. If there was an adhesion model switched on, you would find some settings in this interface. I'm just going to leave everything to the defaults for the sake of this demo and jump right ahead into creating particles. So I'm going to create two classes of particles here. I'm going to create a spherical particle, and I'll just name that as such. And let's just give that a hypothetical particle size distribution. I'm going to give this a top size. Just change that to millimeters. 85 down to maybe let's go down to 25 millimeters, and we'll set that cumulative distribution to be something sensible. Now what I can do as well is I can actually take a preview of the particles that I've created here. Now there's nothing interesting to see here for a spherical particle. You already know what this looks like. Now one of the last things I need to do to set this particular particle group up is assign a rolling resistance. So I want this to behave as if it does have a non-spherical shape, and one of the ways that we can do that is by using a spherical shape or model with a rolling resistance model. So I'm just going to chuck in 0.4 there, and I'm going to go ahead, create a new particle for my lumps, but this time I won't use the default spherical shape. Instead, let's use something like a sphero polyhedron, and we'll visualize that in the particle details view. And so we can change a number of different attributes relating to the size. We can change aspect ratios, number of corners, so I could make this a more jagged particle, for example. But what I'm going to do here is assign another hypothetical size distribution. This time let's go from 400 down to 85 mil. And I'll set this, I want most to be actually pretty small, so we'll go for 30 here. So we'll keep scrolling down the list and create our new particle injection. So this time here, we can see that we've got our two particle groups. What I'm going to do is create two new rows in this list for a singular particle injection. And so we'll create or assign some tonnage for both lumps and spheres. So what did we say earlier? This was an 8,000 ton per hour scenario. So let's just go ahead and break that up. 6,000 tons per hour for spheres, 2,000 for the lumps, and we'll set the entry point to be the feed conveyor. Okay, that's all good. I can skip through all of the other objects that I won't need to interact with. I'll leave the simulation duration to 20 seconds. It's going to be long enough for me. And in the General tab, just make sure that the simulation target is the GPU. And then we're ready to hit start. And so you'll see it'll take a moment to initialize. Gives us an estimate for the number of particles, or the total number of particles in the system. Just flicking back to the 3D view, and we can actually already start to post-process while it's solving. If we use the refresh or the auto refresh tool, we can see it start to render particles into the domain. Now, while this is cooking in the oven, here's one I've prepared earlier. So we'll use this to showcase some of the more basic post-processing tasks. And let's start off by looking at some of the flow perspectives. So, of course, one of the things that we can do is simply just play back the simulation. And by default, what it's going to do is color the particles by a singular color. But of course, what we can do is change the coloring to be one that is based on any of the variables associated to these particles or any particle related data. And so what I'm going to do is switch that over to a velocity contour plot. And then, of course, not just looking at things in a qualitative manner, noting where there's some hot spots, red spots, dark spots, or blue spots. We can also access particle level data or properties through the tree itself. And so what I can do, for example, is let's get the velocity magnitude and let's plot the total average in the system over time. And so we can see, for example, things start to settle after around, let's say that's 10 seconds, sitting at about 3.15, it looks like. And we can do more than this as well. So if we go back to our 3D view, flick to the last time step, I can see, of course, there's a slow buildup of stagnant material in this system, and I can actually extract and identify that group of material based on a threshold of velocity, and I can do that through a new property user process. So I can set that property to be the velocity magnitude. If I set that to a range, let's give it up to maybe 0.1 meters per second. You'll see the particles, the global particles object has now become transparent. I can just switch that off completely, and you'll see that we've identified all particles in the domain which will have a velocity magnitude at that particular time step between 0 and 0.1. And then, of course, I can plot or capture the total particle mass in this collection. So maybe we want to show that in a new plot, as we did for the velocity magnitudes. So this one seems to settle at around 1600 kilos. Okay, so we've had a look at the global velocities, we've identified stagnant material, we can see where exactly material is collecting as the simulation progresses, but we can also look at some more macroscopic quantities and things like flow rates. So what we can do is compare particle mass flows in and out in the entire system. So I'll show that in a new plot and drag mass flow out. And if I plot this on the same axis, you can see that actually for this particular design, it seems as though we have actually satisfied the 8,000 tons per hour. We're not getting any plugging effects, and that's evident through the fact that we don't have any low velocity or stagnant regions around our chute discharge zone. So that makes sense. Okay, so some of the other basic things that we can do is we can understand or get an understanding of the flow behaviors by creating a pathline object once the flow has essentially developed. So once we're out of that initial transient startup phase, which we've already gotten an idea based on the curves that we've generated here, which seem to be pretty stable after 10 seconds. So what I can do is create a new particle trajectory user process. Now I'm going to set my start time to be, let's go to 15 seconds. So I'll just find that in my time toolbar, and let's create that particle selection. Now, in the same way as I can color the actual particles themselves, I can color these path lines, so we can maybe once again use the velocity magnitudes and directly plot that, or the values for velocity magnitudes on the path lines themselves. Okay, so one of the other things we might want to look at is a material spillage perspective. So perhaps we want to make sure that if we have some personnel underneath this feed conveyor, we obviously don't want any material falling onto them that poses a safety hazard. And so what we can do is identify any material that had ever fallen off of this conveyor. And I'll do so firstly by identifying the region of my interest. And so I'll just size this manually through the GUI. So I've identified my zone of interest. We've created that new cube. And I'm going to create a particles time selection, set the range to be all, to grab all particles that had ever entered that region. So we can see actually not that much has fallen through into this region, so that's a good sign, but we can get a more quantitative result by actually tracking the total particles mass in this time scoping. So less than 2.5 kilos fallen off of the feed conveyor belt. So that's good to see. Now, one of the other things that we can look at is more on the boundary perspectives side of things. And so you'll remember that one of the design goals for this hypothetical example is to reduce the wear on the chute liners. And so one of the ways that we can address this goal is by looking at, as I mentioned before when we were talking about wear, by looking at the shear energies. So I've plotted here the cumulative shear energy onto the chute walls directly here. Now, of course, the way that we can get this done is by accessing the object itself, and we'll have a number of different coloring options where we can access all of the properties and the data that's associated with that particular geometry. So we can look at something like cumulative shear energy for an abrasive wear consideration, or we can look at impact energies as well. So we can flick that over to a cumulative impact energy. So, I mean, we can see clearly there's a lot of red zones on this. So you'd better have hoped that your liners had been spec'd to experience this level of shearing. But that's maybe something that we would want to improve upon in the design of this particular system. Now, one of the other things that we can look at is, of course, how the receiving belt is actually loaded. Now, one of the primary things that we mentioned we want to do is minimize non-central loading, which can cause, of course, belt mistracking. So we want to make sure that the flow is symmetric on that belt and centralized on the outgoing conveyor itself. And there are a few different ways that we can look at this particular or address this particular problem by looking at various different things in our DEM model. But one of the things we've already done is switched on that boundary collision statistics module so that we can essentially extract the contact loads, or all the collision forces between particles and the boundaries themselves. And so one of the things you would be able to guess that we would want to be looking at are those contact forces themselves. So we can see here that we could plot nodal forces, Y, Z, X components. We might be interested in the horizontal component here. And we can see it's given me an instantaneous result. And what I'd be interested in looking at is making sure that this horizontal load is equal on the left and the right hand side of this belt, or basically across the midline of this belt. But an instantaneous result might not be the best thing for me to be looking at. Instead, what I might prefer to do is look at a time averaged result. You'll see if I play this back, this is an ever-changing result, and this contour is constantly changing as well. So I can create a new time averaged value. And, well, I've already done this here, so I'm just going to go ahead and delete that. And I'll set my start time to be 20 seconds. Let's grab the average of, let's go for the nodal X force, so that horizontal force component. Again, of course, we can drag that into our display and plot that in. Now, of course, what I can then do is use a mixture of other alternative user processes, maybe something like a plain user process to sum the values across the belt width and ensure that the forces essentially equal each other out. But one of the other things that we can look at is in terms of how the particle is actually sitting on the belt. And what I want to do here is let's switch the particles on in our window. I want to effectively grab just the particles that are sitting in this loading zone. And I want to look at how exactly it is distributed itself onto the belt here. So I'm going to go ahead and again create a new cube and just manually size it through the GUI. And let's just take this as an example. So some of the basic properties that we have access to include the particle size, the particle mass, and we already know the particle material which we prescribed, so we know the density. Now, based on those pieces of information, I'm actually able to grab the center of gravity of all the material that's enclosed within this cube. Effectively, what I can do is grab the center of gravity of the particulate material that's sitting on the receiving belt. And I want to make sure that in the X direction, that CG is not offset from the belt midline. And so you'll see here I've created those user-defined properties, and we could grab the average and plot that over time. And you'll be met with a result that looks like this. Now, if you already know what the X coordinate in the global coordinate system of the belt midline is, then you'll be able to directly make that comparison and define that offset.